Okay, so I thought I was recording and I wasn't, so I gotta redo that. I couldn't remember what I just said. Okay, so right now we're about a third of the way through the semester, a little bit past, and so congratulations for making it this far. I want to tell you how to do problems of this structure. I've loved this style of problem for a really long time because it's actually a very easy problem hidden in the structure that makes it look hard. And you probably already figured this out on the last worksheet, but if you haven't, I just don't want you to be stuck on it again or still. So you have to do distributive multiplication on this problem to get it to work out. And there is an exception if you've already been taught how to use the product rule. A lot of books wait until after the product rule is taught to introduce this style of question, but I'm glad we're introducing it now because the only way out of this mess right now is to distributively multiply, which is the wiser way out. I usually see, let's say maybe 85% of the time, when a student tries to use the product rule to get out of this mess, they usually fail. They just do. And if they do distributive multiplication, they usually succeed. Not always, but the betting is better that way. Let's put it that way. So I'd rather you just do this the safer way and get the points and figure out this question. So there you go. All right, so that's how you do those kind of exercises. Now, you now have a new style of question. It will say something like, if y equals 3x squared plus 2x, find tangent line at x equals 1. Something like that. So this is your new problem type. Very, very common calculus problem, and now it belongs to you. One thing I have not told you, which I need to tell you, is that these derivatives add. So differentiation is what we call a linear function, which means if you take two functions, function f and function g, and like you add them together, so function q is function f plus function g, then the derivative of q is the derivative of f plus the derivative of g. And if this didn't work, it would make your life so much more miserable, trust me. But this totally works. And so now we can go ahead and do this exercise. So first we need to find the derivative of y. And so we need to find the derivative of y at 1. I'm going to just put the letter m there to remind us that's the slope. And we need to find y at 1. And in this case it's 3 plus 2, which is 5. And so what this problem is really asking you is find a line through the point 1, 5 with slope equals 8. Okay? And that's easy. Y equals m x minus x naught m minus y naught. Okay? And if you prefer mx plus b form, be my guest. It's more work. This should be a plus. Thank you for telling me that. I knew something didn't feel right. And then you get 8x and minus 3. That should work. Okay? Okay, advice about any parabolas. When you throw balls, they're parabolas. When you do the economics questions, they're parabolas. The vertex is still at minus b over 2a. It always was, it always will be, and it's going to always tell you where the max or min occurs, right? So if you have something like 4x squared plus 3x plus 7, you can take the derivative, set it equal to 0, blah, 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 and all this song and dance that we're going to be doing really soon. But if I give you a parabola and I say, what's the max or min, you know that the x value for which you're getting a max or a min is just going to be minus b over 2a. Well, this isn't a picture of that parabola, but that's the point. The point is you find minus b over 2a, and then you know the x value where that vertex occurs. So it saves you a whole bundle of work, and if you listen to what I'm saying, just trust me on this, you'll save yourself a lot of time on the homework. Okay. All right, and I think I'm going to let you play with that physics problem. Another recurring theme you should realize is that when you have these, what I like to call upside down parabolas, if one of the roots is at 0, then you know where the vertex is. The question about, where does it hit the ground, you can solve for when this function comes back to 0, and you probably will, and you probably should. But the truth is, and I didn't draw this perfectly symmetrically, so I'm going to cheat a little bit. There you go, something like that. So wherever the vertex is the same time distance because of the symmetry of the parabola. So you can kind of cheat if you know that your function is starting off at 0, 0, hitting a max, and then hitting the ground again. That's going to be the same time difference. But you have to calculate that out the first time before that makes sense. Don't take the shortcut right away, but I'm telling you about the shortcut so when you see that happen, you'll know it's not a fluke. Okay? All right. Now, we have to learn a new rule, and I kind of don't like using it, doing this before teaching you the chain rule, but the chain rule is later in this curriculum. So we have to create a special rule for exponential functions. And that special rule says if you have some base other than e, so I told you if f is e to the x, then f prime is itself e to the x, okay? But there's another thing you can do is you can rewrite functions so they look more like that. So let's say if I say f is equal to 4 to the x instead of e to the x, what I can do is I can rewrite that as e to the natural log of 4 to the x, which is the same as saying e to the x natural log of 4. And then it makes more sense why the following thing happens. Again, but you haven't been taught the chain rule, but I have to multiply by the natural log of 4 in order to make this derivative work out. So this is going to be natural log of 4 e to the x natural log of 4 again. All right, but then this just looks messy, so I mean it's going to look messy. And so we just put this back in its original format, 4 to the x. So why do we have to multiply by natural log of 4? Let me go back to another example, another little rule. If I say f is equal to e to the kx, then its derivative is going to be ke to the kx. So if you believe that, then let's just let this be a rule for now because we haven't talked about the chain rule yet. Okay, so but if you know the chain rule, you know why that's happening. Okay, but this is just a rule for now. If that's true, then it's true that the derivative for this guy must kick out a natural log of 7. Okay, but this is all like the same family of functions. This is all under this e to the x rule. What do you do for e to the x and its family members? Okay, so any kind of base you want can go here, and then there you got a generic rule. Okay? Okay, and there's a little bit of a nasty in the worksheet. This is excessive. Okay, what if you have something like this? You want to take the derivative of that mess? Well, gee, because the base itself is natural log of 14, you still have to take the natural log of it. So it's going to look like a huge mess when you're done. It's going to still kick out a natural log of the base, and so that's what you get. It's okay. It's a stacked natural log. That's really what it looks like. And so, anyway, now you know. Okay, now we get to go on to something a little more, I don't know, interesting, rather than just learning new rules. Okay, polynomial approximation. So just like we can fit a tangent line, so we had this curve thingy, and we said we can fit a tangent line if we know the derivative. So what did we say? We said if we know the derivative at a point, if we have a point and a slope, we can make a new line and call it the tangent line when the slope of the line is the derivative of the function. Yay! So the question is, can we bump up this logic? Can we fit a parabola or a cubic? And the answer is, of course, yes, or I wouldn't be asking the question. So what we want to do is we want to look at this point and we want to say, hey, you know, maybe I can take two derivatives, and then that will give me more information about what's happening to the function there. And this is actually called a Taylor or Maclaurin series if you take this logic far enough. So what we want to do is collect more derivatives that express what the function is doing there. Okay, and let's make up an example and do it. Okay, so I want to fit a parabola to the function f equals e to the x at x equals 1. So how do I do that? So f at 1 is e, f prime at 1 is e, f double prime at 1 equals e. Okay? So we have all the information we need. We need 3 pieces of information like this to fit our parabola. So we need only 2 pieces of information to fit a tangent line, but we need 3 pieces of information for a parabola, and if we want a cubic, we need 1 more. So every time you go up a degree, you need 1 more piece of information. So I'm just going to do this very naive thing and just say I have some coefficients, a bx plus cx squared, and I'm going to see what a, b, and c have to be to make this true. So I want to make sure this matches. So I've managed to pick a difficult problem, but let me see if I can get through it. So is there anything I know? I know when I take the derivative of y, I get b plus 2cx, and I take the second derivative and I get 2c. And since I know the second derivative always has to be the same, this has to be e, so c is equal to e over 2. So that's good to know. Okay, so now I know that this must be b plus e times x, right? Because if I take c, it's e over 2, and then the other 2 cancels out. Okay, so now f prime of 1 has to be e. So now I'm looking over here and I'm going to say, okay, y prime of 1 equals e, and if I put the x is equal to 1 in there, I get b plus e. So I guess I'm finding out that b must be 0. Okay, so that means I can rewrite a plus, and that's 0, plus e x squared. But now f of 1 has to be e, so I'm finding out y of 1 is equal to e, which is a plus e, so a has to equal 0. Maybe this problem isn't as hard as I thought. So my final function should be y is equal to e x squared, and let's see if it satisfies all our conditions. First of all, is it a parabola? Yes. Is f of 1 equal to e? Yes. Is f prime of 1 equal to e. Well, let's double check all this and make sure everything we did checks out, because I just made this up and so I'm kind of feeling nervous about it. So y of 1 equals e. Check. Y prime is equal to e of x, so y prime of 1 is equal to e. That worked. Y double prime is also e to the x, so y double prime of 1 is also e. So I have a parabola and it satisfies all my conditions. And it looks very strange because, well, it's e. Things often look weird when you're working with e. So there you go. Maybe I should give you another example. Maybe not. How about instead of fitting a specific function, why don't I just give conditions? So I could say, just like generically we say, create a line with a given slope and a given point, I can say create a parabola with at -1, 2 with slope f of prime of -1 is equal to -1, and f double prime of -1 equals 1, something like that. Okay, so then you would still say y equals a plus bx plus cx squared, take some derivatives, and there you go. Now I'm going to try to fit these conditions and say, well, at -1 I want the second derivative to be 1. Okay, so we know that there's no x dependence here, so that makes this problem easy down here. C is equal to 1/2. That's the same thing we ended up doing in the last problem. And so then we can bump that back up to the previous level and say y prime is equal to b plus x, and we want y prime at -1 to equal to -1, and then that's b plus, well, x is -1. So b is going to be 0 again. That wasn't intentional. And so now we have y equals a plus 1/2 x squared, and we want to make sure that y of -1 equals 2. So we have one more thing to meet. Y is y of -1. Well, it's going to be a plus 1/2, and then that has to be 2. So a is equal to 3/2. Okay, so we have finally our function. A is 3/2 plus 0x and plus 1/2 x squared, and let's see if we satisfied everything. So let's see if we succeeded. Okay, so we have we can just get rid of all this and just test this outright to see if we got this to work. So we want to see if y of -1 is actually 2. Okay, that one worked. The derivative is going to be x, because the 3/2 is going to drop out. The derivative of a constant is 0, and then we get 1/2 times 2 is 1, so the derivative is just x. So y prime of -1 is -1, and we had specified that, so that worked. And y double prime is equal to 1. So let's see, y double prime of -1 equals 1, and we had specified that. So we got that. We got everything we asked for. We have a parabola. It goes through that point. It has that slope at the same point. We're just using the same point. It would be even nastier if we moved that point around. We're not going to do that in this class It's not typical to do that. Okay, so we're gonna call this a success. And finally, some more hints about the worksheet. These are things you should probably be able to figure out without calculus, and it's essentially review questions to warm you up to thinking about exponential functions again. But when you talk about annual rate of increase, if you're growing at a rate of 2.5% annual growth, how do you convert that into a formula? Okay, so you would say y is equal to p naught, whatever your original thing is, whatever your original value is, times 1.025 to the t, where t is in years. Okay, so that's just to help you sort of get your bearings. Sometimes in these kind of exercises they'll tell you what that initial value is, sometimes they won't, and if they don't give it to you, it's not necessary. Okay, so the question structure on your homework is 2 different countries. You have a certain population to start out with and a certain growth rate per year, and if it's asking which is growing faster in terms of people per year, my interpretation of this question is as follows, is that they're asking about the year. So it's not technically a calculus question. So they probably want you to do it with a derivative. They probably want you to form this thing and say, okay, this is p naught, and this is 1.00 whatever, blah, 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 to the power of t, and then take the derivative and see which derivative is greater. But what I was expecting you to do is to say, wait a minute, the question is stated as growth rate per year, and we want to know which one is growing faster per year or growing faster in that year. It doesn't say which one has the faster instantaneous growth rate. It says which one is growing faster this year. So in that case, you don't need calculus, and all you have to do is take the population multiplied by the growth rate. So whatever, if the population is 10 million or whatever it is, and then you multiply by the growth rate, it could be 0.05, whatever it is, and then you find out how many new people each country gets. So don't overanalyze this question. You don't have to use calculus. I do want you to think about calculus. I want you to think about what's the difference between a growth rate per year and the actual increase in people and how those two concepts intertwine. But I don't want you to overanalyze the question and bring out the big calculus tools, although if you want to, that's totally fine. But I want you to really think about it in a very concrete way, in a very simplistic way. Also, the last question of the worksheet, I feel the same way about also. It is set up as a you could use calculus question, but I want you to think about this in a very low level terms just to get your brain warmed up, and I don't want you to pull out the calculus. To me, this is a review question. It gives you a price trajectory and asks you how fast in dollars per year will this item be growing at the end of 5 years. And I think I just ask you for the new price. So I'm not even asking you for the rate. I'm just actually going to ask you what is the new price. So I want you to think about those last 2 questions in terms of calculus, but the actual exercises in the quiz are very straight up review style questions. Okay? And I think that's all you need for this video.